Week 4 is devoted to polynomials and polynomial functions. So far, we have been looking at linear equations and quadratic equations, and we're now going to expand this to polynomials. So before we go any further, let me just do a bit of framing around what a polynomial is and features of polynomials and the difference between a polynomial and a polynomial function. So here I've got 3 examples of polynomials, but they're ones we've seen before. This one we'd normally call a term, but there's also another fancy name we can give it, and that name is a monomial. Oops, it'd be good if I could spell. 3x plus 2y has 2 terms, and so it's called a binomial, bi meaning 2. And you probably know what something with something that has 3 terms in it, and that is a trinomial. Okay, all of these 3 examples are examples of polynomials. So in other words, poly, when you see the word poly, it doesn't have anything to do with birds and has everything to do with the fact that poly means many. So polygon means a many-sided figure as a shape. Polygamy is when you have more than one husband or wife. And a polynomial is an expression that has more than one or more terms, to be more precise, I suppose. Just a side note, a trinomial is a quadratic when it's got an x squared, an x, and a constant term. So this is a trinomial, but it's not a quadratic. But if I wrote 3x squared plus 2x plus 5, that would be an example of a quadratic expression. I'm not sure, I can never remember why it's called a quadratic when it's only got 3. I'm sure there's some really good reasonings for it. Maybe you can research that if you are keen to. So what's the difference between a polynomial and a polynomial function? Not a lot. It has multiple terms, but a function, which we're going to do in the next unit, but a function is often written as a dependent variable. In this case, I'm going to call it P, that takes on an independent variable, which is almost always X, but it could be any letter. But that takes on the independent variable, and the rest of the expression is written in terms of the independent variable. So it's a function because this is like the input to a function, and P of X is the output of the function. Now, I'm going to go a little bit fancy-schmancy here to try and get you to think generally rather than specifically. And the general way I'm going to express this is by using some sort of subscript notation. So just bear with me as I talk you through this. So it's a polynomial function. We've got a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus all the way down to a2 x squared plus a1 x plus a0. So what we have here is descending powers of x. That's what that notation means. The reason why we're using this notation of a sub n, it stands in for a number. And because we've only got 26 letters of the alphabet, and a polynomial might have more than 26 terms, unlikely to come across one, but it could do, using this notation allows us to say these are separate terms. And there could be any number of them. So the subscript just says it's the one that goes with this term. This is the one that goes with this term, and so on. Now, there's a few things. I should point out number 1, where a sub n does not equal 0. So it means that there is a starting term. If that was equal to 0, then this would be the starting term, right? Because this would all cancel out. So there's some sort of starting term. Everything else could be 0 or any other number. So it could be 2, could be -7, could be 0, or it could be pi, which is a constant number. But they're all constant numbers, fixed numbers. And then at the end here, we have a constant number as well. Okay, so that's one other thing that should be pointed out. The constant, it's called the constant term. Okay, so I'll put that down there. It's called the constant term, the term without a variable in it. And you should note that the constant term might be 0. So whenever we see a 0, it's basically invisible in the expression, but it can always be chucked in. Hope that kind of makes sense. Now, I want to look at some examples and probably make more sense to you. There's a couple of phrases that's really important for you to be across. Number one, the leading term. That's basically, no, I'm doing a different color. That's basically a to the power of n, x to the power of n. That's the leading term. In other words, it's the term with the highest power of x, if you want to be more precise, the term with the highest power of x. I should point out that some polynomials might not be written in this order. X to the power of n might be on the right, or it might be in the middle, but it can always be rewritten in descending powers of x, and therefore this term becomes the leading term. Okay, so it's the highest power of x, not the leftmost term, but the highest power of x. The degree of the polynomial is n, i.e. the highest power. When I go through some examples, it might help you understand that a bit more. Okay, one last thing I should have pointed out is that n has to be a natural number. So that means a whole number, a counting number, anything like that. N could be 1, n could be 4, could be 267. As long as it's a counting number, then you're good to go. You can figure out why it can't be 0. And maybe if you remember your index work, you might be able to work out why it can't be a fraction and why it can't be a negative number. So let's have a look. Let me keep it zoomed out now, I think. Let's have a look at some examples before I wrap up this video. P of x is equal to 7x to the power of 7 plus 3x cubed plus 1. This is a polynomial. It doesn't have to have every single power, because this kind of means 7x to the power of 7 plus 0x to the power of 6 plus 0x to the power of 5, 0x to the power of 4 plus 3x cubed plus 0x squared plus 0x plus 1. Okay, you would never write that, but you can always pad it out with zeros. Okay. Pause the video and put down what you think the leading term is and what the degree is. Okay, so leading term, 7x to the power of 7. The degree of the polynomial, so degree of p of x, is equal to 7. One more example. P of x is equal to 2x plus 1 plus 3x squared plus 14x cubed. It's not written in the right order, but it could be. So from this polynomial, we could say that the leading term, we just need to scan across and see the highest power, 14x cubed, and then we can say the degree of the polynomial is equal to 3. Non-examples. Be careful. Basically, it might look like it's a polynomial when it's not. Here's some obvious non-examples. P of x equals x to the power of negative 2 plus x squared plus 1. The power of negative 2 is a dead giveaway. P of x is equal to x to the power of a half minus 2x squared. Not a polynomial, because one of the powers of x is a fraction. P of x equals 3 on x plus 2. Not a polynomial. because if the x is on the denominator, it's actually x to the power of -1 in this instance. So it doesn't have a positive. It's not a natural number power. So be careful that you have that it can't be rewritten in a way which gives it a negative power or a fraction power. One more example, I think, and that is p of x is equal to x root x plus 7. If you remember, root x means x to the power of a half, and therefore it does not have a natural number as a power. So these are all non-examples. Now, last thing I'll do in this video, and this is all just orientation to polynomials and polynomial functions, two functions are said to be equivalent, are the same under what conditions? Well, two polynomials are the same or equivalent if their corresponding coefficients are equal. See this funny old phrase here, that IFF, it's not a spelling mistake. It's mathematical short speak for if and only if, which means it works both ways. So the phrase is their corresponding coefficients are equal. So for example, I'll pick a dumb one. P of x equals 3x squared plus 2x plus 5x minus 1. And Q of x is equal to 3x squared plus 7x minus 1. P of x is equal to Q of x. Because, and I won't write this down, so if you're not watching this with the video, it's going to be a bit of a problem, isn't it? Because the x squared coefficient is 3, so these coefficients correspond. 2x plus 5x is 7x, so if I simplify this, I get 7, and so this 7 and this 7 correspond. And the minus 1 and the minus 1, the constant terms, are equivalent as well. So because each of the coefficients are equal, we can say that the polynomial functions are equal. And note that P and Q are very commonly used as how we describe the function, as is f of x equals, can often be called a polynomial function as well. Okay, I'll leave this video here as it is just an introductory one, and next time we'll have a look at some operations to do with polynomial functions. Try.